Welcome back, guys, and those of you that have been following along know that we're at the point where we're going to start designing our ESP8266 light switch schematic. So let's get started. Let's start up fritzing and go over to the schematic view. So a few quick things that you'll notice are all the different sections that are here for the parts. So the most important one is core, because all of these parts will most likely be used in most of your regular projects, such as resistors, transistors, capacitors, switches. All of these things will be used very often, so that's why these are included here in the core parts. So if you scroll all the way to the bottom, you'll see there's a schematic view for the core parts, and you'll see there's a power. Let's grab that, bring that out here, and let's rotate it. Let's make it 12 volts because that's the amount required for working with our LED strip that we're using. Let's grab a ground and bring it out here as well. Let's rotate it. Alright, so what I'm going to do now is I'm just going to go ahead and place everything on the schematic view, and I'll fast forward through it, and once I'm done, I'll explain everything. Alright, now that I'm done, let's take a look at what's happening in this circuit right here. So, as you can see, this 12 volt power supply is basically powering everything in this circuit. So one thing that we needed to do was we needed to make sure that if we were going to use just the 12 volt power supply, we needed to use a voltage regulator so that we wouldn't fry this ESP Wi-Fi module. This is because the ESP Wi-Fi module has a voltage limitation of 3.3 volts for its VCC, and if you go over that, it's going to blow the board. So we needed to use this 3.3 volt voltage regulator, and that basically fixed everything. So to get this ESP Wi-Fi module to work, you need to connect the 3.3 volts to VCC, which basically powers the board, and you need to connect the 3.3 volts to the CHPD pin right here. So what this basically does is VCC powers the board, so it will give power to the rest of this, and CHPD turns the board on. So if you have VCC plugged in but not CHPD, the board will be receiving power, but it won't be turned on. So CHPD basically acts like an enable pin, and it turns the board on. It was recommended by the manufacturer to include a 10 kilo ohm resistor to limit the current that flows into that. So that's why I included this resistor right here. So now basically why we needed to include the rest of this circuit right here is because the ESP itself cannot power the LED strip, and these three LEDs and this current limiting resistor are basically just simulating the LED strip that would be there. So because this 3.3 volts right here coming off of the ESP cannot power the LED strip, we need to include a relay system so that we can power this LED strip. So what we needed to do was we have this relay right here that that's connected to this pin all the time, and when you activate the relay, it will flip and it will get connected to this pin right here, pin 3, and it will power the LED strip. So how this works is when you send a pulse down the coil, this will flip. This needle will flip to this side. And so what happens is, let's say I activate the ESP Wi-Fi module from my mobile app and I turn it on. So GPIO2 right here is high. So what that will do is then it will activate this transistor right here, and it will allow current to flow from the coil, activating the coil, and to ground. So what that does is once this coil is activated, this needle will be flipped, and it will be connected to pin 3, which will then let current pass from the 12-volt power supply to the LED strip to ground. This will activate the LED strip and those will work. That's why we need this transistor right here. If you have a power transistor, you can basically avoid the entire relay circuit, because then you can just connect the transistor in series with the load, which is the LED strip. But since the transistor that I'm using is just a basic BJT PN2222A, it doesn't have that high a current tolerance, and due to this, I decided to use the relay because I had a couple sitting around. So one last thing that I'm going to talk about here is this Schottky diode right here. So this is very important in any circuit that has a coil, as you can see right here. You need a Schottky diode to be placed in the reverse direction of the coil. This basically behaves like a flyback diode, and it makes sure that when you take away power, so let's say that this was high, so let's say GPIO2 was high, and current was flowing through the coil and to ground. And you suddenly turn off that GPIO2. This will cause a voltage spike right here in this coil, and what this Schottky diode does is it makes sure that this this voltage spike cannot harm any other device or component in this circuit. And this diode should be a Schottky diode. It's a special type of diode that has a very low forward voltage drop, and it does very quick switches. So I recommend using a Schottky diode. If you don't have a Schottky diode, you can use a different diode, but it wouldn't be preferred. So that's basically it. Comment, like, subscribe. Let me know what you think, and stay tuned for more.